Hello everyone and very warm welcome to all of you at this amazing session at PW. My name is Aman, your favorite maths buddy. And what are we doing in this session? In this session we are going to revise something. What kind of revision, sir? Now we get multiple requests from you guys that you were struggling with the revision part. So over here we have come up with a revision series where we will be revising each and every chapter. Now, because making notes is out of fashion these days, so I believe that many of you would have missed out on making notes. So this is the ultimate session where you can make up all the concise note of this particular chapter. So which chapter are we going to cover today? Today we are going to cover the chapter of real numbers. Real numbers? Do we have unreal number as well? Yes, we have unreal number as well. We'll talk about them as well. So let's start and then only we can understand what are we going to learn. So for today's session, the only focus would be on one thing. What is that thing? That is the fundamental theorem of arithmetic. To be very honest, there is nothing in this chapter. This chapter is a cakewalk. Whatever we have learned till now, we have to revise that all. What things we have learned? Since this is a chapter related to number system, so we have to understand first of all the types of number, then operations on number. So what kind of operations? Basically, we have learned about the highest common factor, lowest common multiple, all these things. So that all will be covered in this part. The topic for today would be this thing as usual, and we would be talking about the application of this thing because this thing on its own is very simple. When I'll show you the slide for this particular topic, you'll say, so why are we doing this at the first place? So be patient. We'll start with the revision first. Revision. So what we need to revise, as I told, every class, every grade, when we come to the first chapter, it relates to the numbers. And numbers, we have listed a list of number over here. So first thing first, natural numbers. So if we are learning about the numbers at the first place, let's understand where does the number come from. So this is very simple to understand. Visualize this in manner. Humans in the ancient time were having food scarcity. Now, whatever food they have, they had to estimate for how long they can keep it. So for that they used to do the counting on fingers. Okay, on fingers like this, which we also do. This is a very primitive style, right? So they used to do the countings on fingers. Later they evolved themselves. What kind of evolution happened? Now they realized sometimes the fingers were very short to do the calculation or estimation for big numbers. So they came up with the idea of telemarks. Today we know by the name of telemarks. At that time we were not having an idea what exactly is telemarks. What exactly is telemarks? I hope you know. If you don't know, let me recall it for you. Sometimes what happens, on the stone they used to carve line like this. So what does this resemble? This is not something else. This is just 1, 2, 3, 4. As simple as that. And for 5 they used to cross it like this. So this entire thing used to depict 5. In this manner, they can go on depicting 6, 7, 8, 9, 10 and the numbers as usual. Again, this theme seems to be a very primitive style to me as well. So what happened over a period of time, they realized they can put up numbers. So they came up with some notation like this 1, 2, 3, 4 and they helped us in counting. Now, since these numbers helped us in counting and these were the very starting of the numbers, we started calling these numbers as natural numbers. So natural numbers were very simple to understand because they were counting numbers. But what happened after that? Why we are having a long list of numbers? It's very obvious. It's just like you and me. If we are doing some work, after doing the work, we realize that we could have done the work better. So we named a file new name and then start adding something to that part. So same thing happened over here. Now, while we were talking about natural number, we missed one thing. Humans didn't understand the concept of nothing. They didn't got the idea that someday they'll not be having anything. So anything basically means nothing over here. So nothing is simply the idea of zero. So if we don't have anything, we might say that we are having zero. So 0 when included to the set of natural number is called as whole number. Now the name itself again suggests whole. So they thought that they have the complete set of number and that is why they called this as whole number. So whole number is 0 included to the set of natural number. Then again some confusion erupted. What kind of a confusion? Let's say I was sitting over here at my home, not here, somewhere over here. Understand, just visualize. So I am sitting over here. My school is 2 kilometers down the line over here on this side. And my playground where I go to play football is something over here, exactly 2 kilometers. Now, if someone asks, where is your school? 2 kilometers. Where is your playground? 2 kilometers. So how would I differentiate between these 2 kilometers? So for that we have to get an understanding of directions. So this 2 kilometer in this direction and exactly opposite 2 kilometer on this side we are having my playground. So 2 kilometer, this I gave the direction as positive and this one as negative. The better way of understanding this is temperature. Now I hope you have some understanding of science as well. Temperature is nothing but the degree of hotness or coldness. How so? Now today it's very hot. When I am dictating these terms over here, I am getting sweat. So basically the temperature is on a higher note. Sometimes if I go to a very cold place, I feel that I should go on vacation to Leh or Ladakh. Over there, why? Because the temperature over there is very low and sometimes it goes below zero. So what is this below zero and above zero? Above zero is the degree of hotness basically, and below zero is showing you that the temperature is very low. That means it's very cold out there. So in the similar manner, the magnitude of the number 1, 2, 3, 4 and so on remains same on either side of the zero. On this side it becomes positive, on this side it becomes negative. So positive and negative is just depicting you the direction. That was about integers. Why I have narrated such a long story? Because from this we come to the part of real number, which is rational and irrational. So were these unreal number? No, these were real numbers. They were just a part of these two. So these two and specifically rational. All this whatever we have learned is nothing but rational number. Rational number is a bigger fish which is consuming the smaller fish. So these are all smaller fish consumed by the rational number. Alright, I hope you are getting my point over here. Now, since you have learned about rational number and irrational number, I need to go to the next slide and talk about them in more detail, right? So let's understand about rational number first of all. Over here it is written real. Why? Because rational number are also part of real number. That's it. So rational number, when we talk about them, first thing which comes to our mind is P by Q. So why this P by Q? Because the numbers are represented in P by Q form. And over here we have 2-3 things which we need to remember. Like what? First thing is it need to be represented in P by Q form. Then what are these P and Q? So P and Q both are integers. P and Q both are integers. If you couldn't have learned about the integers at the first place, you wouldn't have known about rational numbers. So that is why each and every step is important. Today, whatever effort you are doing while watching the video and making the notes, this would be helping you going into the next grade and understanding about unreal numbers. Alright, so P and Q would be integers. And one final point over here would be that Q should not be equal to 0. Q should not be equal to 0. If these 3 points are there, you can easily understand whether the number is rational or not. Now, this thing is fine. If I write a number 3 by 5, this is rational. If I write a number minus 4 by 7, this is rational. Now, but this is the fractional form. We have learned about P by Q. This is the fractional form. What about if a number is written in a decimal form? Let's say 0.25. What about this, sir? Now, written in decimal form, that also might be a rational number. We need to understand when it might be a rational number and when it should not be. So when I say about P by Q form, we need to understand whether when I convert this fraction into the decimal form, the decimal would terminate or not. Terminate. So when I write 5 by 2, what happens? I hope everyone can do this division. 2 dividing 5. So over here 2.5 would be the answer. After 5, sir, now we have got the remainder as 0, no need to go further. But there might be a case where the number can go on like this, 3.33333. Would this end anywhere? No, the dot over here simply signifies that this is never ending thing. This is a never ending loop. So something goes on loop and it goes on and on and on. So over here, 2 things came up. First point, if the decimal is terminating, if it is terminating, that means it's ending. In that case, I can call it to be a rational number. And in the second case, if it is repeating or you can say recurring, in that case also you can call it to be a rational number. So about the decimal form, these 2 decimal form will work for rational number. They will be called as rational number. But other than these 2, it will not be called as rational number. I'll come to the part what I am talking about. But first we clarify over here. When I say about any other number like natural, whole or integers, all are part of rational number, just like rational number are part of real numbers. So now coming to the part where we have a decimal which is neither terminating nor repeating. So let's talk about that as well. That is called as irrational. That is called as irrational. Now when we have to study irrational, things are very simple. Why? Because the numbers which are not rational are irrational. That's it. So any number which cannot be represented in P by Q form, that would be called as irrational. In the fractional form, it is that easy to understand. Or if I talk about the decimal thing, if I code a decimal like this, 1.4756259812, and the number is still going on. Now, when I wrote this number, I had this thing in mind that this number should not terminate and the number should not repeat. And over here, you cannot see a pattern also. So basically, the number which is not terminating and non-repeating, that will be called as irrational number. What is this NTNR? Is this some hero's name or what? This is simply non-terminating, non-repeating. That's it. This is how you can easily remember about irrational number. So this was about irrational number. So what about real numbers? We haven't talked about the real numbers yet. So to understand real number, here we have a slide which will show you the sum of entire thing which we have talked about till now. What is the slide, sir? So real numbers are nothing but the combination of irrational and rational number over here. Rational number which are depicted by letter Q over here. Irrational numbers are here. Now, in rational number, we have further division. We have non-integer rational number and we have integers. What is this differentiation basically? So up till integers, when we were learning that sequence of integers, we realized that the numbers were always intact. So if I say I had one pizza, I consumed one pizza. If I had two pizza, I consumed two pizza. Is that the case every time? I hope if there is the devil, then that would be the case. Otherwise, normally what would happen? You would stop somewhere. Somewhere would be the stopping point for you. You will eat 1.5 pizza, right? 2.5 pizza, 3.5 pizza. It's not always that you will be consuming the entire piece. So we are having part which are fractional and we missed on that part, and that is why we have integers and non-integer rational number. So if I write 1 by 2, which is simply 0.5, that is nothing but a non-integer number. So these are non-integer integers. And coming to the very basic, we have integers positive as well as negative. In positive, we have one more number which is 0. I hope you remember 0 is neither positive nor negative. And finally, we have in whole number, natural and 0, which I already talked about. So this table was nothing new. I hope that these 5 minutes or 10 minutes, whatever time has been already done, it would be fruitful for you, or for some people it would be very waste effort because you already know. But to make sure that the basics are intact, it was important to convey this much of information. So what next? Now in grade 9th, you have learned something about Euclid's division lemma. I'll come to that. I even forgot that I brought a question related to this part. So over here we have a product of non-zero rational and irrational number. A question being asked, if we have a non-zero rational number and an irrational number, and if you multiply, basically product is nothing but multiplication. This is very simple to understand, right? So product of non-zero rational and irrational number. What would you get? Would you get a rational number, irrational number, rational or irrational? Is that a possibility that you can get both? No, that's not the case. So over here, let me start assuming the number. Let me say that 3 is a rational number. 3 is a rational number, right? No one would be saying that, okay, no sir, this is a whole number or this is a natural number. This is a rational number. So 3 being multiplied with root 2, which is for sure a irrational number. Irrational number. If you have any iota of doubt, what is this iota? You can search on your own what is this iota. So root 2, which is an irrational number, multiplied with a rational number, what will you get? You will get 3 root 2, which is again an irrational thing. So I haven't done anything over here. The point I was making was that if you have iota of doubt that root 2 is irrational, towards the end of the session, I'll talk about the proving part of irrationality. Root 2 is why it is irrational. Alright. So be patient, be towards the end of the session as well. You'll understand. So over here, I have one realization that if two numbers are being multiplied, one being rational, other being irrational, always, the final product will be irrational. There is no doubt about this part. If two irrational numbers would have been multiplied, then You can think on your own, something you should think on your own. So this is the activity left for you. Now I proceed further. Which I was talking about, equate division lemma. Division lemma, right? It's not dilemma. Dilemma whether I should attend the session or not. No, you should. You'll get something new over here. Now lemma, what is this lemma? Are you aware about lemma? Lemma is nothing a logical statement. It's a logical statement which helps us to derive a further fundamental thing. So what fundamental thing? I'll talk about it. What exactly does this division lemma says? It simply says if we are having two numbers, let's say we are having two numbers A and B. So if I divide A by B, what will happen? If I divide A by B, so basically what would happen? A quotient would come. I'm writing it as Q, and some remainder would come like R. So this is the long division which we generally do. So this is all we have in division lemma. I told you we don't have anything special in this particular chapter. So I'll write this in this form. A is equal to B into Q. B into Q plus the remainder part. It can be 0, it cannot be 0. And in this one addition is there. What addition, sir? The B part and the R part, they would be a relation. So remainder would always be greater or equal to 0 and would always be less than B. Why? Now, if you are dividing any number, let's say if you are dividing 2, not 2, if you are dividing 3 by 2, so what would happen? You will do the division 1 times 2 and you will get a remainder as 1. So 1 over here is less than 2. If I would have got 2 as the remainder, then I would have gone for further division and ultimately I'll get the remainder 0. So remainder would always be less than the number with which we are dividing. So I hope you remember this thing. Dividend equals to divisor multiplied by quotient plus remainder. This is what we know about this division lemma. But why are we learning this division lemma? This is a very simple thing you already know. So for that we have a next thing to answer. Division algorithm. Division algorithm. Now algorithm is a very factual statement which will work always. So how do we use it? We use this part to find out the HCF. Now is the time to think about it. What is HCF exactly? HCF, highest common factor. So if I talk about any number, so let's assume something. Let's assume 2 and 3. Now, which number can you think of which can divide both 2 and 3? Can you think of it? At least think of one if you are not able to. Because 2 and 3 are basically co-prime and there will be only one number. Co-prime? What is this new number I am talking about? Co-prime basically means when the HCF is 1, then the two numbers are co-prime. So 2 and 3 are having HCF as 1. Where I am talking about HCF? Because using this division lemma, we can do the calculation of HCF. How, sir? So let me give an example for this one as well. Let's take two numbers. We are having two numbers, one being 130 and another being a special number, 420. Alright. So here we have to do the division from 130 dividing 420. How do we find the HCF? By the long division method. We are going to find the HCF using two methods today. One by this division lemma, another by the simple method which we are going to learn. Be patient. So here we need to do the division. 3 times will be 390. I hope you remember the times table. This is 0, 0. This is 30. Whatever remainder we have got, first thing notify this part that 30 is always less than 130. So 30. Now what we need to do, divide the number, this number with which you were dividing at the first place by the remainder. So 30 being divided by 130. 30 being divided by 130. So what will happen in this case? So 4 times is 120. Here we have the remainder as 10. I hope each and every step is simple over here. 130 and 420 we are trying to find the HCF, and 130 we divided 420, whatever remainder we got. Then from that we have divided 130. And going further, whatever remainder we have got, we will divide 30. This is nothing new. We have already learned in class 9th. If you haven't, in that means that you haven't given the exam properly. Some flaw must be there. So over here dividing by 10, we are having 30. So I hope now you remember how the division will go. Ultimately, you'll get the remainder as 0. Now the number with which you finally do the division, that means the number over here, which is 10. The number 10 over here is your HCF for these two numbers. This is how it is being proceeded. And this is the application of Euclid division algorithm. But sir, this is all what we have already done. What's new in this chapter? So be on the mark now. We are talking about what new in this chapter. And we'll say there is nothing new in this chapter. This says, fundamental theorem of arithmetic says that every composite number can be factorized as a product of prime number. We are not good at English. Can you translate in mathematics? Let me. 6, which is a composite number. With number which is not prime number which are having only two factors, the number itself and 1, like 2. 2 is a prime number, 3 is a prime number, 5 is a prime number. And composite number which are having more than two factors, like what? Here are having 2 into 3. So these are only two factors. I hope you remember the number 1, which is the factor for each and every number. So 6 basically is a composite number which can be written in the form of product of prime. 2 and 3 both are prime number. And exactly this is what this fundamental theorem of arithmetic says. So who gave this theorem? There was a mathematician who is known by the name of Gauss. He gave this theorem. Now you would be saying, what's a useless thing he gave? At this point of time it seems very simple, but when he gave this theorem, it was a huge achievement. And such an achievement, he was called the Prince of Mathematics. Can you believe it? The Prince of Mathematics. There are 3 princes of mathematics. I have told you the name of one. You can try and find out the other 2 princes of mathematics. This is a job for you. I hope you have the interest in mathematics and you will do it. Alright. So we have 6 as 2 into 3. This is exactly what this fundamental theorem of arithmetic says. It simply says that every composite number will be written as the product of prime numbers. The order can vary. That means I can write 6 as 3 into 2. It's basically the same thing. There is no difference at the first place. Alright. So this is what fundamental theorem of arithmetic is. Very simple thing. Alright. Nothing new over here. So you can take up any other number. Let me write 27 over here. 27 is what? 3 into 3 into 3. Basically 3 cube. So 3 into 3 into 3 is 27. You can write 8. That is 2 into 2 into 2. Again 2 cube. So I have a fascination of cubes. You should find out. So over here we have the number which has been asked to prove that this is composite number. So how can we do the proving part? We should go with MCQ. Sometime in the examination they ask subjective questions, so you should be prepared about that as well. Composite number. Now how we need to proceed? To prove that the number is composite, I told you the fundamental theorem of arithmetic. And what it says composite number is the product of primes. So basically you need to prove that this entire number given over here can be written in the form of the multiplication of prime numbers. So let me see, over here one hindrance is there, this addition sign. So let's work on this one. First of all, 13 is over here. If you are able to see, we are having 13 at 2 places. We are having 13 over here. This is one 13, this is another 13. And in between we are having addition sign. So what I can do, I can take 13 common over here. When I take 13 common, now I can write this as 7 into 11 into what? Into, this will be simply 1 plus. Now this is, I am putting a bigger bracket over here. Plus this 13 is again taken common, so plus 1 over here. So what are we left with? This is 13 into 7 into 11, 77. 77 plus 1. Now what? 13 into 78. I hope you are good at calculation, because it's important. Even if you are not, then also you have to do the calculation. You cannot escape it. So 13 into 78 over here. Now 13 is what kind of a number? It's a prime number. What about 78? I hope you remember something. What is that? 78, you can do the prime factorization. So how do we do that prime factorization thing? It's very simple. You have to start with the division and with the first prime number. The first prime number is 2. So you can go on dividing 78 until unless you get 1. Everything I am not going to do it. It's not a regular session. It's a revision session. So I hope you are having some task on your hand as well. So this is what the number composite can be proved. And most importantly, this is what the application of the fundamental theorem of arithmetic looks like. Other than that, anything else is there? Yes, as I was mentioning the term application. So, since what we have done, we are talking about the composite number, we are talking about the factors. So, that exactly we are going to use over here. Irrationality of number. We can prove the irrationality of number using this theorem. We can talk about the terminating decimal expansion of rational number. I mentioned this part. How do we get to know whether the number is rational or not? So, this again is the application of fundamental theorem of arithmetic. And lastly, HCF and LCM. Again, the same thing came. HCF and LCF also have a relation with this fundamental theorem. How? It's very simple. I already told you 6 is nothing but 2 into 3. So factors we are talking about, composite number, product of two prime number. That is how, as simple as that. So this is basically a very simple thing. The theorem on its own hasn't talked about any new thing which you haven't known yet. Alright, so let's talk about the application part and quickly wrap it up. So here we are talking about the terminating decimal expansion. What do we mean by terminating? The decimal ends over there. When I told you about 5 by 2, I mentioned that the final answer would be 2.5 because the decimal over here terminated. After this, we don't have anything. Fine. But how do we get to know every time that the decimal terminates? For that, we have a straightforward thing. What is that straightforward thing? If we have this in the form of factors, then every time we'll be getting a terminating decimal. I am writing over here 2 raised to the power m into 5 raised to the power n. Sir, m and n is nothing but basically they are just numbers, basically a natural numbers which we are resembling over here. 2 raised to the power something, 5 raised to the power something. If you have this thing in denominator, then we are very sure that the decimal expansion of that number will always be terminating. So if I write a number a upon 2 raised to the power, let's say 2, and b raised to the power, not b, over here we have 5. So 5 raised to the power 3. I'm pretty sure over here that the final expansion a would be some number, don't worry. So this number finally would be terminating. Alright, are you getting understanding over here? So this part is important in the denominator to make that number terminate, This was one thing which we have already talked about. Other than these two numbers, no other number should be there. For example, if 3 occurred over there, if 3 occurred somehow, then the number will not terminate. You can check on your own by dividing 1 by 6. Or if you have difficulty, how can we divide a smaller number? Divide 10 by 6. Divide 10 by 6 and you will realize this part. Why I am saying so? The reason is very simple. 10 upon 2 into 3. I told you the factors in the denominator should be either 2, 5 or both 2 and 5. Apart from 2 and 5, nothing should be there. Here we have 6. That means we are having a factor 3, which should not be there. So this was one thing about termination. These two and only these two should be there. Nothing else. Sometimes the examiner can be very smart. Now how? This is one thing ahead of you. Understand this part. Now they might ask you by giving a big number, asking you how many places after the decimal would terminate. Now this is an important thing. When you see about the factors over here, 2 raised to the power m and 5 raised to the power n. Now it can be 2 raised to the power 3 into 5 raised to the power 3. It can be 2 raised to the power 4 into 5. It can be 5 into 2 raised to the power 1. Simple thing. So basically over here, what we can decide how many places the decimal will terminate just by seeing the factors, over here. The power will decide. The highest power in m and n, the highest power in m or n, whatever be the highest power, at that decimal places the expansion will terminate. A very important thing. Just by viewing m and n, you can decide whether the decimal will terminate after how many decimal places. This is something new which I am telling you over here. I hope you have already made a keynote in your notebook because that is important. Something new should be always be noted down and see the application of as well. So this was about the terminating part. Very simple, nothing new because you have already done this part in grade 9. So I am not delving much more detail over here. Next thing, HCF. Already talked about, sir. Why are we talking now? First of all, we have talked about the equivalent division lemma. Through that method we learned. Now this time we are going to learn about HCF through fundamental theorem because we have to show something. Now we have learned something in the first chapter. So that is why. Since we know that a composite number can be written in the form of prime. So we'll be having factors. Now, if we have two numbers, let's say we are having number 12 and 16. Both composite, agree on this part. You can write the factors of these. 12 is 2 into 2. 2 into 2 is 4. 4 into 3 is 12. What about 16? 16 is basically a square number. You can always write it. So I'll write in the form of prime numbers. 2 into 2 into 2 into 2. That is how you can write it. What I have done over here, you might have written 16 as 4 into 4. Don't do it. When we are finding the HCF, make sure that you write the prime numbers only. And best thing would be if you write them in the form of powers. Like this, here we have a pair of 2. So 2 raised to the power 2 and 3 is alone. So 2 raised to the power 2 into 3. Here we have 2. How many times? 1, 2, 3, 4. So 4 times. So we have 2 raised to the power 2 multiplied by 3, 2 raised to the power 4. Now, according to the definition, or I would say the method which we know, the product of the smallest power of each common prime factors in the numbers. Not getting anything. I'll help you out. They're basically saying that over here we are having the prime factors for both the numbers. If you want to find out the HCF for both the numbers, or if we in case more numbers are also there, we need to focus on the common factor, each common factor. Now, what common factor do we have over here? We have only one common factor, that is 2. Alright, so we have focused on each common factor. And what power should we take? Because over here we have 2, over here we have 4. So we should always be taking the smallest power. So I hope everyone knows this part, that 2 is smaller than 4. This is very simple thing. So we need to see the common factor, only the common factor, along with the power which should be the smallest. So over here the HCF of these two numbers would be what? 2 raised to the power what? The smallest number 2. So that is it. That means 4 is the HCF of 12 and 16. You can verify as well. So 4 is the highest number. Which can directly divide 12 as well as 16. After this, we don't have any number. You can try dividing by 8, but that will not work for you. This was about HCF. Next thing would be LCM, lowest common multiple. Now we are talking about the part of multiple. So multiple is basically the multiple of 2 is what? 6, 4, 8, all these are multiple. The multiple of 3. So I hope if you don't remember the concept of LCM, over here you can understand it. We are having two numbers, 2 and 3. We are talking about multiple. So multiple basically is the lowest one which can be divided by both 2 and 3. Over there we were dividing by that number. The factor was dividing the two numbers. In the case of multiple, since it is multiple, we would be dividing that number by these two numbers. So the LCM of these two would be what? It is 6. If you don't know, you'll get to know by the method. So it is 6. So if we divide by 2 and 3, both will work. And this is the lowest number. 6 is the lowest, because after 6 we are having multiple numbers. For example, we have 12. 12 can be divided by 2 and 3. We have next number 24. 24 can be divided both by 2 and 3. So lowest common multiple. This is what lowest common multiple is all about. What does this method says? Again, let's take the same numbers. We are having 12 and we are having 16. This time I hope we can directly write the prime numbers, 2 into 2 into 3, and this is 2 into 2 into 2 into 2. Alright. Now, we can write in the form of powers. So let me write in the form of powers to get the more clarity. This is 2 raised to the power 2 multiplied by 3. And over here 2 raised to the power 4. Fine. 2 raised to the power 2 and 2 raised to the power 4. What we need to focus on, let's read in the definition. Product of the greatest power of each prime factors. In the previous definition, we talked about common factor. Over here, each. We need to consider each. So we have basically 2. We have over here, we have 2 as well as 3. These are the prime factors. So both 2 and 3 are there. And which power do we need to consider? 2 or 4? They say the greatest power we need to consider for each of them. So for 2 we are having 4, and for 3 we are having only 1, because only 1 3 is there. So the LCM would come out to be, the LCM of these two numbers would be, for 2 we are having the highest power as 4, and for 3 we are having only 1 3. So this is 2 into 2 into 2. So you can do the multiplication, I hope. I hope you are comfortable doing it. So you can do the multiplication, give me the final answer later in the comment section. That you can do, I hope. So over here, this is how this LCM things work. This is how this LCM things work. Now, to make sure that whether you have understood this part or not, what we need to do? We need to do few questions which will help us consolidate the concept. Here we have a very simple question asking about the HCF and LCM of 15 and 24. So I hope you can pause the video and try doing on your own. But if you are not, I'll definitely do it over here. So for 15 and 24, you need to write the factors. 15 is nothing, 3 into 5, 24 dividing by 2, we get 12, again dividing by 2, we get 6, again divided by 2, we get 3, so multiplied by 3. What I have done? I have done the prime factorization. If you don't know how to do the prime factorization, please do by this method. It's very important. Now, what I mentioned that you always write this in the form of powers, So this is over here 3 into 5, it is as usual because the power are 1 and 1. In this case, I can rewrite this as 2 raised to the power 3 into 3, right? 2 raised to the power 3 into 3. First step, do the factors. Second step, write the factors in terms of power. Finally, what we need to do? We need to find the HCF. Alright, let me rewrite HCF over here. HCF. For HCF, the simple method was, if you haven't understand, please listen carefully. For HCF, we need to focus on only common factor. 3, 5. Over here, 2 and 3. The common factor we have is only 3. 3 is common to both. Because 2 is not here and 5 is not here. So 3. And what is the lowest power of 3? Anyhow, we are having only 1 and 1, 3 and the power is 1. So we are having HCF as 3. That's it. HCF part done. For LCM, we need to consider each and every factor. We are having 3, we are having 2, we are having 5. So all 3 would be considered. And the power would be the highest one. For 3, just now we have seen only 1 power. For 5, you can see over here, we are having only 1 power. And for 2, we can see the highest power is 3. So into 3. So basically 3 into 5, 15, 15 into 8. I hope you can do the multiplication and find out the number as 120. And you can see the options as well. The final answer over here is given as option number B, which is 3 and 120. This is how we can do the calculation for HCF and LCM. This is how we can do the learning process using the fundamental theorem of arithmetic. One final thing in HCF and LCM, there is a relation between the numbers and HCF and LCM. What is this relation? The numbers, when you multiply them, when you take the product, they will be equal to the product of the HCF and LCM which you have found out. Now how, sir? You can do this on your own by taking these two numbers. When you do the multiplication of 15 with 24. So finally, whatever you will be getting over here, same you would be getting when you do the product of HCF of these two numbers, that is 15 and 24, with the LCM of these two numbers, again talking about the same number, 15 and 24. So this is a direct formula. But you have something on your side that which you can work upon. What is that? When you try this for two numbers, it works well. But what about if you have three numbers? What do you have? Three numbers. Let me warn you at the first hand over here. It will not work for three numbers. You can find out the relation for three numbers. I hope you can do this. Another activity I can give it to you. What activity, sir? If you have given the numbers in the form of fraction, then what? Then also you have to do the research on your own. Alright, I'll not give you two things at the same time. Let me talk about one. If I have to find out the LCM of three numbers or the relation of three, A, B, C, in that case, what will we do? We'll do the multiplication of these numbers as usual, A into B into C, and we'll multiply with the HCF of these three numbers. A, B, and C. And in division, what will be having? We'll be having HCF of any two numbers, A and B, multiplied with HCF of any two number after this. That means B and C, and finally the HCF of the last pair which was left, that is A and C are left. So this is the formula which we can use when we have three numbers. I told you for two numbers that formula works, but that formula does not work when we have three numbers. When we have three numbers, this is how the formula works. That means the LCM of the three numbers would be equal to what? three numbers being multiplied as usual, multiplied with the HCF. This thing over here seems to be very common. The denominator is different. In denominator, what we are doing? HCF of the three different pair which will be formed using the three numbers given to us. Similarly, we'll be having for HCF as well. I hope you can do this much of a research from your own, that you can write this, complete this expression over here. Alright, so I'll leave you on this note and talk about one final application which was left, which is irrationality. But we have to solve one more question on this. Let's talk about this one. We have 39 and 91, the HCF is equal to 13, the LCM they are asking about. Now, one way of doing it is you can find out the LCM of 39 and 91, but just now we have learned the formula, let's make the use of it, right? So, let's make the use of it. It is 13 into LCM which we need to find out. What I have written? HCF into LCM equal to the product of two numbers, that means 39 into 91. 39 into 91. Now, I hope everyone is good at multiplication. What happens over here? The number 13 goes on the other side. We have 39 being multiplied with 91 divided by 13. Over here, 13 cancelling out 39 three times. And writing this as 273. Which option? Option number B, sir. So basically B is my favorite or what? Most of the options B are correct. Don't fall in this loop over here. So do the calculation correctly, remember the formula correctly, and make sure that you are noting it down. The part which I am telling you and the part which I am not telling you, because there should be some suspense, right? So that suspense should remain and you should do some research on your end. So moving to the next question over here, which is again asking about the relation of HCF and LCM, but in a different manner. Every time the formula will not work. This time the question is the product of HCF and LCM of the smallest prime number and the smallest prime number and the smallest composite number. So you should have idea about prime numbers, you should have idea of composite number, only then you can answer the prime and composite number which are the smallest. So I hope you remember that the smallest prime number is 2. What about the composite, smallest composite? After 2 we have 3, but wait, is 1 also composite? No, 1 is neither composite nor prime. So never consider 1 either to be prime or to be composite. It is not belonging to any of the category, just like 0. 0 is neither positive nor negative. So next number after 2 is 3, but 3 is prime number, sir. So next number would be 4. So these are the two numbers for which we need to find out the HCF and LCM. Let me tell you directly over here. HCF would be simply 2 and LCM would be simply 4. Now, when you do the product of these two numbers, you will be getting 8 and 8 will be the answer. So, you have solved very quickly, you haven't given some time. You should have paused the video and tried solving on your own, because right now I have to solve it. It's important. So, this is how we need to proceed with the product of HCF and LCM, and we have the formula for relation as well. And this is the application of HCF and LCM through fundamental theorem of arithmetic, given by whom? Alright, so one final thing about proving the irrationality. This is the final application, and bear for a few more minutes because this is the end of the session over here. Now, when I talk about irrationality, one theorem should be very clear to us. The theorem says if we are having a number a square, this number a square is divisible by p. If this a square is divisible by p, which is a prime number, that is why I have denoted with p. So, in that case, a would also be divided by p. What I am saying, if we are having a number square which is divisible by a prime number, so in that case, the number itself would also be divisible by p. You can take this, you can assume it to be, let's say, 4 square if divisible by simply 2. So, what happens? So, 4 would also be divisible by 2. That's it. That is what this theorem says. As I told, basically theorems in this chapter are just the stating of the obvious thing. So this is the obvious. Why I am dictating right now? Because it will be used in the proving part. So what are we going to prove? I told in the very starting, if you are not convinced that root 2 is an irrational number, now is the time you will be convinced, because now we are going to prove root 2 is irrational. By what method, sir? The method is known as the method of contradiction. Just like we contradict ourselves, we say something and we do something. Hypocrisy. So over here we'll be having the method of contradiction. How will we start the problem? Root 2. Root 2 we will be starting by assuming it to be a rational number. rational number. We are assuming that root 2 is a rational number. But sir, we know it's a irrational number, and that is why this is a method of contradiction. We are assuming, we are not saying that this is a rational number, we are just assuming that this is a rational number. Now what happens when I say any number to be rational? You remember when I told you the definition of rational, I told you rational numbers are the one which can be represented in the form of P by Q. So I can write root 2 as equal to P by Q. Now since this root is not looking good, to me, I'll square on both the sides. So squaring on both the sides. So what will happen with this squaring? When you do the square, this root will be evaporated. We will be left with only 2. And over here P square Q square. So P square upon Q square. Now this expression doesn't look good. I have to write something upon. So no need to write something upon. Let me transfer this Q on other side. So we'll come up with P square being equal to 2Q square. Right? P square is equals to 2Q square. Alright, it's very simple thing. When I write this P square is equal to 2Q square, I can write in other form as well. It doesn't matter whether you like it or not. I can write in this form as well. Q square is equals to P square by 2. P square by 2. Alright. So Q square over here is P square by 2. So basically this P square will be divisible by 2. Right? This will be divisible by 2. Over here one thing I have missed out on when I assume this to be rational. In rational number, P by Q form is there always. But P by Q form is specific over here where P and Q are both co-prime. Both are co-prime. So this is important. You should always note down in your notebook. Over here P and Q are co-prime in this case when we are starting this assumption, because it will play an important role. That is why I am telling, otherwise no need to state a fact over here. So P and Q are both co-prime, and over here I am seeing that P square is divisible by 2. If P square is divisible by 2, we have learned a theorem. If P square is divisible by 2, that means P will also be divisible by 2. Now when I say P is divisible by 2, so that means I can write P in the form of 2A. Why, sir? If any number is divisible by 2, that means 2 will be a factor of that number. So I am writing 2 as a factor and other being the factor, A being the other part. So it's like I can write 16 as 2 into 8, right? Because 2 is the factor. So P is nothing but 2A. Now I can replace the value of P equals to 2A. We were having the expression over here, P square is equals to 2Q square. Let's put over here. So Q square equals to P square. This was the thing. So over here I am replacing the value of P. That is nothing but 2A whole square, which will leave us with 4A square. Now this 2 and 4 seems to be relative in some form. So I'll cancel it out and I'll be coming out with Q square being equal to 2A square. Again, we are having something 2 over here and I can transfer it on the other side because I have something with this. So this comes out to be A square being equal to Q square by 2. We have reached to the same thing which we had with P. So now what we are going to do? Q square being divided by 2. So that means I am writing over here. If Q square is divisible by 2, in that case Q will also be divisible by 2. And I can write Q as 2B. Right? Q can also be written as 2B. Let me replace the value of Q also, since I have done for P. It's getting very long, I know, but it's a very simple process. This is how you have to remember it. There is nothing other than this. So writing the value of Q as 2B, replacing the value of Q as 2B. So we would be having P square was 2A whole square divided by, I am writing this as P by Q, and Q is nothing but 2B square. One thing is very sure over here. We have come up with 4A square divided by 4B square. That means the numbers are not co-prime at the first place because they are having the factors, common factors. They are having common factors. P and Q are having some common factor. That means at the very starting, whatever we stated, that was incorrect. What we stated? We stated that the numbers are co-prime and the number is rational. So over here we have realized that the numbers P and Q are not co-prime, Since they are not co-prime, I can say that what we have assumed was wrong, and hence if what we assumed was wrong, so that means that root 2 will be irrational. Anything which is not rational is irrational. So hence we have our answer, and hence we have done the proof part. That is all we have in the proving part. I hope you have understood it. It's a very, very simple thing. Each and every step you have to just remember, and remember very logically. When I say remember, it doesn't mean you have to mug it up. Remember logically. So that is about the irrationality part, how we need to prove, and each and every question you will go by this method. Other than that, we have one or two final things which we will use over here to understand whether the proving part over there you were conscious or not. So the question over here says, in the proof of irrationality of root 2, the contradiction arises because we cannot find, what we cannot find? What we cannot find over here? Integers p and q such that root 2 is p by q. I hope even if you haven't listened to me carefully, but one thing would be very obvious in the entire explanation, and that was co-prime. That was co-prime. So we cannot find co-prime integers p and q such that root 2 p by q. And just because we were not able to find that p and q were co-prime, we came to the conclusion that the number was irrational. And hence the answer over here is not irrational. The answer over here is co-prime. If the number would have been co-prime, the number would have been rational. One final question and I'll leave you once and for all. It says, which of the following numbers is not irrational? A very simple thing. Why towards the end of the session, sir? Can you apply your mind and quickly tell me which is the number which is not irrational? Because in each and every option I can see root. So wherever we have root, we think that this is irrational. But that's not the case. We have to see root 3 is there, 2 being multiplied with root 3. That's perfect. That's irrational because they both are the number, one being rational, one being irrational, always irrational. 8 root 4. Sir, over here also the same thing, sir. One number is rational, other being irrational. No, see carefully, root 4. What can we do for root 4? Root 4 is nothing but root 2 into 2. So that means I can take 1, 2 out of this. And root 4 directly you should also know is 2. Very basic thing I am talking over here. So this is 8 into 2, which is 16, which is a rational number because I can write it as 16 by 1. And over here I have realized this is the number which is not irrational. So basically this is rational, and this is asked in the question because they were saying not irrational. Alright, things simple, and as usual, because everything what we have done today is something related to class 9th what we have learned. So on that note, I'll not take any more time of yours, but this was the first session in this series. In the upcoming session, we'll be revising this next chapter and the next chapter following it because we have covered multiple chapters. I hope you have enjoyed it, but even if you haven't enjoyed it, make sure that you have made the proper notes of this part, or you go and practice few problems that makes you comfortable in this particular topic of real number. Sir, but you didn't told about the unreal numbers. Yes, you will get to know about the unreal numbers when you go into the next grade of 11th, where you will understand about complex number, the numbers which are not real. So you can do the research on your own. What are complex number and how are they different from real number? So another homework for you. On that note, I leave you over here. Have a great time. Enjoy yourself. Bye bye. Meet you some other time.